about graph-based stream processing. So I'm gonna cover a few topics, actually. The first one is graphs in general, what kind of data structure it is, what do we use it for, what are graph analytics, and how they can help us uncover insights from our data. And then to put everything in context of real-time analysis. So using graph analytics to perform stream processing on continuously incoming data. For the purpose of this talk, me and my colleague created a simple demo application that performs some kind of stream processing on a Twitter dataset. I'm going to show you the application and the architecture behind it, so you can get a better overview of how this stream processing is actually done and implemented. So let's dive right in. This is me. As already stated, born and living in Croatia, currently in the capital city of Zagreb. I got my master's in computer science from the Faculty of Electrical Engineering and Computing in Zagreb. My field of study was social network analysis. That's what my master thesis also focused on, applying machine learning techniques to further the analysis of social networks. I'm currently pursuing a PhD at the same faculty, and I work as a developer relations engineer at Memgraph, a graph analytics company. So if you never heard of the role, that's okay, me neither until I started it. My job is essentially to make the life of developers easier. So I create demo applications, code snippets, proofs of concepts, anything that could help bootstrap the development process of other developers. Aside from my work and my studies, I love to travel, I love to cook, and I definitely watch streaming platforms too much. So not only Netflix, but HBO and Amazon are almost certainly always on. So let's dive into the actual content. So we're going to start with the graph data model and what graphs are and where we store them. So graph databases. If you're not familiar with it, this is a graph. So we are not talking about charts. We are talking about the data structure that consists of nodes, relationships, and properties. So these are nodes, person, person, and city location. Each of these nodes has a label on it, so it can define the entity a bit better. So this is a person node representing a real life person. Other than the label, it also has properties, key value pairs that assign some other kind of information to it. For example, here it has the name and a string with a value Harry. This is the date of birth. Again, we can have different kinds of properties. They can be strings, integers, floats, date times, and so on, like you might find in any other database. And these nodes are connected via relationships. Sometimes you will hear the term links, maybe edges. Throughout this presentation, I'm going to use the nomenclature nodes and relationships. So, for example, looking at these two nodes, they are connected with a relationship lives in, and this relationship again can have any number of properties. So here is duration in years, which represents for how long this person has lived in this location. So this is probably one of the simplest graphs you could imagine. And if you're wondering about the description beneath, labeled property graph model, it's how we define this kind of graph model. So it has labels on nodes and properties on nodes and on relationships. These kind of graphs are stored in graph databases. You might have heard of some. Memgraph is, for example, powered by a graph database. Neo4j is probably the most popular one. Then you have dgraph, tigergraph, and a lot more have risen throughout the past few years as the whole field has gained in popularity. So what's the difference between a graph database and a relational database, aside that the graph database stores graphs? So the main difference, as you can probably already tell, is that the relational database consists of tables. So In most use cases, one table represents one kind of entity or the relationships between them. So here we have product, and the rows are actual products, while this order table combines product, suppliers, locations, and customer. What does that mean? It means that you need to join these tables to get a clear picture of how a product is connected to a customer and to a supplier and a location. You need to perform SQL join operations, and then you can find out what relationships are present in the database. In a graph database, the situation is completely different. All of the relationships are part of the data itself. So for example, you have a customer node, and this node directly references another node, for example, location, and it's connected via a relationship. This relationship has a type. Here it is resides at. So it's much simpler to find the relationships in a graph database as they are modeled directly with the data itself. Another key difference is that graph databases don't have a strict predefined schema. For example, here in relational databases, you need to define these tables, what kind of attributes, columns they have, and you kind of can't stray away from that model. Later on, if you need to extend it, change it, this becomes a bit problematic. In a graph database, the model is not predefined. You can define it yourself and you can enforce it. But for example, if at any point you decide to add another property to just one node or part of the nodes or relationships, you can do that. The database won't stop you. So if you are working with dynamic changing data and you can't define a schema beforehand, maybe you don't know about some information that will be added later on, graph databases offer a lot more flexibility. The conclusion is, if you have a data model that consists of a lot of relationships, the data is interconnected, then graph databases are probably the way to go. There are definitely many use cases where graph databases are a hit and miss. For example, if you're storing static data in key value pairs, if you're logging something, if you're not gonna apply any advanced graph algorithms on it, then there is of course no point in storing your data as a graph. So now that we know that the data is stored in a graph database, how do we communicate with it? The most widely used query language for graph databases is called Cipher. You can think of it as SQL for graphs. So it has a lot of the same constructs, for example, clauses such as match, delete, set, return to interact with the data. There are functions, mathematical ones. There are also functions that parse data. And you can also define custom procedures, for example, in Python, C, C++, or Rust. Once you define these procedures and implement them in these languages, you can then call them from the Cipher query language, so you can extend its functionalities. So here you can see the difference between a Cipher query and a SQL query. They perform the same task. It's a recommendation engine. So here in Cipher, maybe you can follow, we have a customer and it's referenced as customer 1. And this customer bought a product. Okay, and now we try to find all the other customers that have bought the same product, and we check which other products they bought. Now that we have all of these other products, we check which of them weren't already bought by customer 1, and the rest of them we can return as recommendations. If we try to do the same thing with a SQL query, it gets a little bit more confusing and complicated because of the aforementioned join operations. So we need to join different tables together. We need to match the attributes, the columns in each table, and it just becomes very hard to keep track of what's happening. So this is a use case, the recommendation engine one, that's perfectly suited for the graph data model and the Cipher query language. Now I'm just gonna mention graph analytics, why we use graph analytics, what it is, for example, algorithms, traversal techniques, and so on. What do we perform on these graphs? So graph analytics, also called network analysis, generates insights from the relationships in a network. So we analyze the data, we analyze the relationships between entities, and we try to infer some kind of insight from it. What can these algorithms be? You have probably heard of some of them. For example, PageRank, the algorithm implemented by Google, breadth first search, depth first search, very famous interview questions on coding interviews, the shortest path algorithms that try to find the shortest path between entities, all kinds of community detection algorithms, and so on. So everything here falls under the term graph analytics. Why use graph analytics? These are some of the companies that are also using them for very specific tasks. Google implemented the PageRank algorithm, which measures the importance of web pages based on how many other web pages are pointing to them. So if you ever done a Google search, you have encountered graph analytics. Facebook uses community detection algorithms to find densely connected groups of individuals in its network. Amazon uses collaborative filtering algorithms for product recommendations in real time, such as the Cipher query I showed you before. And Pinterest and Uber Eats are very good examples of applied graph machine learning. So aside from graph algorithms and graph traversals, there are, of course, graph machine learning techniques as well that are tailored to work with these data structures. Normally in machine learning, you work with vectors, but here things get a bit more complicated. But on the other hand, you get a lot more info from the network than you would from vectors. So this is a social network. And what we can do here is perform community detection algorithms to find which users are more connected to each other. Then we can make recommendations on what other users they could be friends with. We could do machine learning techniques like link prediction to find out which users also could have a connection between them. And Facebook uses some of these techniques in its own platform. This is a very cool example. This is a black background, and what is visualized are connections between people in the Facebook network. That's why you can see the outline of the world map. It's also not surprising that larger parts of the Amazon rainforest, the Sahara, are grayed out because they are not very densely populated, and larger parts of China and Russia because they use other platforms aside from Facebook. Recommendation engines are a perfect use case for graph algorithms and graph analytics in general. You can traverse the relationships in this network and then try to find out which entities are connected to each other via some other entities. We can check if one user likes one genre in specific, what other users also like that same genre, and then find the movies they have recommended, they have rated as good. It becomes much easier than when working with tables. Supply chain management, this is a business use case. Here we can do risk analysis. We can check which suppliers are most likely to cause a break in the supply chain. And once this data is visualized as a graph, it becomes much easier to keep track of all the connections in the chain itself. Fraud detection is probably the most adopted graph use case. A lot of companies have implemented such a system. Here is an example of a credit card fraud network. It becomes very easy to find all of the transactions that were executed on a compromised POS device, or for example, to track where one card has made transactions. We can use graph algorithms such as community detection to detect rings of fraudsters, people who are working together to perform fraud. We can use centrality algorithms to find the most influential nodes or users in the network to check how they are influencing its behavior. And now that we covered some of the most important graph use cases and where graph analytics can be applied, I'm gonna talk about stream processing and graph stream processing to be more specific. So what is stream processing? It's the process of analyzing your data in real time, in the simplest terms. So you have some kind of source for your data. These can be IoT devices. This can be a platform, for example, a web shop. This can be any web application that's tracking user behavior and so on. And all of this data is being generated each second. And what you will normally do is you will save this data in a database and then analyze it in batches, perform your algorithms and get the information you want. But with stream processing, what we are doing is we are sending the data directly to a stream processing engine, and we are performing algorithms as the data is being ingested in the engine. So these can be dynamic algorithms. For example, they take into account the context of the previously ingested data and try to come up with new information based on that context. They don't go over the whole data set, that will take too much time, but rather they try to only focus on the part of the network that's being affected with the new incoming data. So once the stream processing does its magic, the results can then be visualized, they can be used for further processing. The data itself could be enriched. For example, if you're calculating the PageRank value of new nodes that are being streamed into the engine, then we can add that calculated rank to the nodes themselves before saving them to another database or to the same database. We can also send the data back in the form of a stream, for example, through Apache Kafka or Pulsar or RabbitMQ for further analysis or to be ingested by other services or applications. I mentioned dynamic algorithms. Why do we use them? Because sometimes it's not possible to analyze all of the data at once. If you have a very large data set and try to run the PageRank algorithm on it, it will take a few minutes, maybe even hours. It's not feasible. That's why we implement dynamic algorithms that only work with real-time data and try to make fractional calculations and approximations that are as good as possible. So to reiterate, stream processing is a type of big data architecture in which the data is analyzed in real time. It is used whenever you need to extract additional information from your data as it's being consumed, and the processing happens asynchronously. The data source and the data stream processing work independently without waiting for a response from one another. So here on the previous image, these two services, they work asynchronously. So when new data is ingested in the stream processing engine, the data source is not informed of that. So everything happens here and it has no effect on the data source itself. That's what it means. So where does Memgraph fit in? Memgraph is a platform for graph computation on streaming data. A lot of words. What I actually mean is that Memgraph is a graph database. So a database designed to store data in the form of graphs and to run graph algorithms on this data. But it also has connectors that can ingest data from real-time sources such as Kafka or RabbitMQ. And then you can run graph analytics, graph algorithms and traversals on this data as it's being ingested. So Memgraph is a stream processing engine in this context. You use it to store graph data in memory. Why in memory? Because when you're performing stream processing, time is the most important resource you have, and you need to perform it as fast as possible as to not get any congestions in your data analysis pipeline. So that's why in-memory architecture is definitely a big plus. You run graph analytics on it, and essentially you analyze the streaming data. One other product I'm going to mention is GQL Alchemy. If you've heard of SQL Alchemy, you can think of it as the counterpart, but with a Cipher query language instead of SQL. It's a Python library, open source. You can use it to connect to the graph database. And instead of writing Cipher queries directly, you can use Python objects and paradigms. So you create classes, you can build Cipher queries with Python methods, essentially bringing all of your work into a Python script or a program. It has OGM capabilities. OGM means object graph mapper. Just like SQL Alchemy is an object relational mapper, you have the query builder that lets you bypass the Cipher query language and work directly with Python on disk storage. As I mentioned, Memgraph uses an in-memory system, so there are a lot of properties that are maybe too large to be stored in memory. You don't want to use up all of your RAM, so you store some of the properties on disk instead in a relational database or a key value store. And graph schema validation. So as I mentioned before, graph databases don't enforce a strict schema. You can't define it, but you can define it in GQL Alchemy. So you create a schema in the form of Python classes, and then when you try to save data or load data from the database, this schema will be checked, and you will get an error if it's if it doesn't correspond to what you have defined in it. If you want to play with it and try it out in Python, I have created a Jupyter notebook. That's pretty easy. You can just power up the graph database and start the Jupyter notebook and go through it. So the stream processing architecture. This is the demo application I was talking about that I will show you. And this is what it looks like architecture-wise. We have a data source, and the data source are tweets that we scraped in December. So we scraped a lot of tweets that had a hashtag Christmas. We wanted to find the most Christmassy person on Twitter at one point. So we created a CSV file with all of the tweets and retweets. And now we're going to mimic a real-time data source because we have this CSV file. I created a Python script that's going over it, and each second it's sending a message to Apache Kafka, which is acting as our message broker in this application. So Kafka gets a message, and Memgraph is subscribed to that Kafka topic and ingests this message once it's created. So there is a tweet, it gets sent to a Kafka topic, and then Memgraph ingests it. It performs some kind of algorithm. I will show you which algorithms later on. And once it's finished, what it does, it sends back the results to another Kafka topic. Why are we doing that? So that our web application, a Flask server, can also subscribe to the same Kafka topic and ingest the results. So now that we have the results in our backend, we can send it to our front-end client that was created with React, and we can visualize the results themselves. So this is a very basic overview of the architecture. Later on, if you have any questions, of course, you can write them in the chat or ask me directly. So now it's demo time. I'm going to show you the application. You will have to bear with me for a few seconds because it will take around a minute or two for everything to get set up. The application is being built at the moment with Docker. If you haven't heard of it, it's a great product. You can run your applications in the form of containers, and you can orchestrate them. What I have created here is a few services, as was shown on this picture, and all of them are actually their own Docker service in their own container, and they are being set up right now without me having to do anything in the background. So now let's just start a front end as well. This service was separated for convenience sake. Because it's a React application, it will also take a few seconds to power up. And if I haven't mentioned it before, aside from React on the front end, another library was used, a D3.js. It's one of the most popular visualization tools JavaScript has to offer, and we use it to visualize most of our graphs. So now we are waiting for the data to be ingested. Okay, here it is. So what's happening right now, as you can see in the console, is this is my Python script that's generating messages. So here you can see that each message is actually a user on Twitter that has retweeted another user. I'm gonna show you the data set. This is one of the simplest I could come up with. So we have users, Twitter users, and each of these users has only one property, a username, and it's unique to each user on Twitter. And how are they connected? They're connected with a relationship of the type retweeted. So each user retweets another user, and that is our network. And what we are trying to find out is which user is the most Christmassy one. So which node is the most influential one in the network. How are we going to do that? By using the PageRank algorithm. Just like Google uses it to rank web pages, we thought that calculating the PageRank value of each user would also tell us more about their influence inside this Twitter network. We are using the dynamic implementation of the PageRank algorithm, which means data is being analyzed in real time as it's being ingested. The same goes for the algorithm, the other algorithm we are running, and that's the community detection algorithm. We are trying to assign each node to a community. So each user gets gets a number that represents the community they belong to. Again, it's a dynamic algorithm, which is being run on real-time data. So how does it look like at this moment? As some of you may have probably guessed, the radius is not random. It depends on the rank that was calculated. So the largest node, the one with the largest radius, is the one that has the largest PageRank value. So the username is World Music Award. And at the time that we were scraping Twitter, this was the most influential and the largest and had the largest follower base. So it had a lot of retweets. Some of these nodes are changing sizes. Why is that happening? Because as new nodes are being ingested in Memgraph and being analyzed, they are getting a new PageRank value. So once the new value is calculated, it also gets sent to a Kafka topic, and then it gets visualized here. Yeah, it's changing constantly. And down here, you can see the community detection visualization. For example, this is the largest community, as you can see by the coloring. The community detection algorithm is based on propagation. So each time a new node gets added to a community, the algorithm tries to check if it needs to adjust the communities that the other nodes in the network belong to. So this is pretty cool, but I will also tell you a bit more about the underlying implementation. So what is actually happening? First, what we need to create in order to perform this kind of analysis is a transformation module. It essentially means that we are mapping the incoming messages, these ones are actually in JSON format. So we are mapping them to Cipher queries. So how can the graph database create this message in a format that it understands? Each message has a source username. It represents the Twitter user that has retweeted another user, and this one is defined with target username. In Cipher, we do it with a merge query. You can think of it as a create query. It only checks beforehand if the node exists, and if it exists, it doesn't create it again. Otherwise it gets created. The same applies for the relationship. That's why we use a merge instead of create. So we create a user node and we assign it only one property, the username. We also create another node, that's the target one, and then we create a relationship between them. User one retweeted user two. And with this transformation module written in Python, there are only a few more lines that I chose not to include in this image. And with this transformation module, we tell how Kafka messages are mapped into a graph. Okay, so now that we are creating the graph, while the messages are being ingested, we need to perform an algorithm. We are creating a trigger that will execute each time a new node gets added to the database. So what will our trigger do? This is a PageRank trigger. So we tell the graph database, run the dynamic PageRank algorithm each time there is a created vertex. So vertices are nodes when there is a created edge, or when a vertex or an edge is deleted, because that changes the relationships in the network. Once the algorithm comes up with a rank, we assign it to the node. So we enrich the data itself. We don't not only store it to the graph database, we also add a rank to it for later use. And another thing we do is we send this newly calculated rank to a Kafka topic, because it needs to also be visualized in our front-end client. So the backend server, the Flask server, needs to read it from a Kafka topic. This publisher is another Python module that just has a few lines of code, and it takes this node and rank and it sends it to the Kafka topic. So once we have created the triggers with a PageRank algorithm, and in a similar fashion with a community detection algorithm, we can create and start a stream. What does that mean? We need to tell the graph database how to connect to a Kafka stream. We give it a name. We tell it which topic it should listen to. This topic was called retweets because the messages were essentially only retweets. And transform, this is the transformation module. We defined at the beginning how these JSON messages should be mapped to graph objects. And we tell it where the Kafka server is located. This will usually be an IP address, but as we are using Docker to orchestrate everything, we can just use the service name as the address. Once we have defined the stream, we just create it, and then we start it. Once this command gets executed, Memgraph starts ingesting these messages from this topic, and they're being saved in the database, and the PageRank algorithm and the community detection algorithm will be run every time there is a change. The triggers will get executed. And there is one last step, and that's creating a trigger that will send each newly created object in the graph database also to a Kafka topic. So because we want to visualize everything in our application, we also need to get info about the nodes and the relationships between them. That's why this trigger executes every time there is any change in the database, and it sends the data to a Kafka topic, so the Flask server can also ingest it, and so the front-end client can visualize it. To reiterate, first step, we create a transformation module that maps messages to graph objects in the graph database. Then we run the graph analytics algorithms or traversal techniques that we need, in this case, PageRank and community detection. We created them with triggers. so they can fire automatically, but you can also execute them from Python scripts every so often. You can define the time, you can do it manually through a command line interface or through our visual user interface. And once all these algorithms are set up, then we can create and start the actual stream. So the data can start flowing in from the data source and end up in the stream processing engine. And then all the magic with the algorithm happens. Because of this specific application, we created another trigger that sends all of the data and all of the algorithm results back to another Kafka topic, so it can be used by other services. In this case, the Flask server and the front-end client. These are the visualizations. Again, the D3JS library, big recommendation. It's definitely one of the simplest ones to use. They have a lot of other features, not only visualizing graphs and networks, but charts and other objects. It definitely becomes easier to manage them and handle them once you learn how to use it. And what we have done as well, if you want to play with a data set, I have shown you the Twitter one. You can visit Memgraph Playground. So these are graph database instances that were prepared in advance, and you can just play around with them from your browser. So no need to install anything. You can just try to write Cipher queries to see how they function. So this is a Cipher query that calculates the PageRank value for each node in the database, and it returns a list of usernames ordered by their PageRank value. So it's the same data set that was used in the demo application I showed you. So World Music Award has the largest rank in the whole network. Now let's return 100 users that have retweeted the user World Music Award. As you can see, Cipher queries are somewhat intuitive. User 1 retweeted user 2. We use where to filter the nodes. We say, okay, user 2 needs to have the username World Music Award, and then we return all of the nodes that are actually connected to the user World Music Award. If we visualize it in the form of a graph, you get this, and World Music Award at the center of it. And that's more or less it. Thank you very much for your attention. I hope I didn't bore you to death. I hope there are questions. Sometimes this can be a challenging topic, as it combines graphs, graph analytics, graph theory, stream processing, event-driven development. The demo application, even though it's simple, it took quite a few hours to be created, because there are a lot of parts that are working with each other. They are constantly ingesting data, creating data. It's very easy to have problems in the data analysis pipeline. It gets harder to debug these problems. So it is a bit advanced, but once you get a hang of it, actually once you create your first application, it definitely becomes a lot easier. And yeah, you can check out our GitHub repositories. Here, this is the link of the demo application. It's also open source under the MIT license. You can download it. You can use the code for anything else, and maybe it can help you jumpstart your own development process if you want to play with it. If you have any other questions after this session, you can join our Discord server, and there are a lot of other users who are doing stream processing with graphs, like-minded individuals. If you have any questions, this is definitely the best place to get answers. And here are my social handles. If you want to connect, always open to it. You also have the link to my LinkedIn profile and Zoom chat. Definitely hit me up if you have any questions, suggestions, whatever. And that's it for me. We can start with the Q&A if there are any questions.
There are questions in Q&A. Maybe you can read them if you don't mind.
Of course. Oh, there is another tab. Wasn't used to this. Where can I find your YouTube channel? I think this is meant for. This wasn't probably meant for me.
Oh, yeah, our team will share the YouTube channel again, so you can subscribe there.
Nice, thank you. What are the prerequisites for graph networks, resources for graph networks? The prerequisites in terms of the knowledge you need to have beforehand, nothing. As you have seen here, the graph data model is pretty simple, pretty intuitive. Literally, once you create your first graph model, your first problem with a graph, a network, you get a hang of it. I mean, there are a lot of pitfalls. There are a lot of details to get right later on once you're dealing with, for example, billions of nodes and relationships. But if you're talking about millions, it's very hard to get it wrong. So you can just dive right in. I have shared a few resources here. You can go to our documentation site. Probably the best site to get started with is this playground one. Let me show you this. If you're interested in graphs and the graph model, you can just start with begin with Cipher. These are guided lessons that tell you how to use the Cipher query language, how to write queries, what you get as results, then you can edit them. It's definitely much simpler in such an online environment than having to download something yourself, coming up with the queries yourself. This is probably a lot easier. Let's open up the other questions again. In a classical database, each relationship either exists or not. Okay, didn't get it if it's a question. Is there a successor to Memgraph that can work with quantum computing databases? No, I don't think anyone is working in this realm. And if you know something else, or if you find out at some point, definitely ping me. I will be very interested to read about it. A comment from Joel, very interesting. I'm curious as to why some of the other outer nodes in the largest network in the community graph were on a different color than most nodes in that network. So as I said, it's a propagation algorithm. So it relies on the neighbors of one node to assign community to it. So for example, the most basic example I can come up with is you have, for example, a few nodes that are connected and the algorithm assigns them communities by random, and each of them has a different community, is colored differently. Then the propagation algorithm goes from one node to another and tells them, hey, this node has this color, it's in this community, you're close to it, maybe you could join it too. And then that node gets that community, and so on and so forth, until some kind of condition is met and the propagation stops. If the outer nodes, they don't have a lot of connections, maybe they don't have any connections, they are isolated. That's why they sometimes get assigned completely separate communities that are not present anywhere else. Some algorithms are a bit smarter, and they not only take into account the relationship between nodes, they also take into account the properties on the nodes themselves and the label of the node. And that's why some of them can have a different color, even though they are connected to a lot of nodes with the same color. There are still some kind of attributes that make it distinct. When not to use graph networks? I mean, when it's best to use relational database? There are a lot of use cases. I mean, there are probably more use cases where you should use relational databases than graph databases. If you, for example, have an enterprise application and you already have a predefined table schema for it, you know what the data will look like in 2 years. It won't change that much. You are not analyzing it in some crazy fashion. You're just trying to retrieve information from it. So for example, you have a platform with users that register on it. If you're not running graph algorithms on them, then you only need a relational database that's going to tell you, okay, this user has this username and this email and so on. You're just kind of retrieving simple information from the database. Then you have key value stores that are only supposed to store one type of data without any relationships actually behind them. If you don't have any relationship in the data model, then it makes absolutely no sense to store it in the form of a graph, because it would only be nodes that are not connected with anything. You can't run any kind of graph analytics algorithm or traversal technique on them. There are also a lot of other use cases. There is actually a blog post I have written on this exact topic. Maybe I can share it here. Graph databases versus relational ones. And good to see that it's ranking first on Google. One of my greatest accomplishments so far. Here you can check some other use cases when graphs are appropriate and when relational databases are appropriate. And now let's see if this main chat has any questions. Can we connect it using Kafka Connect? At this point, I actually don't think so. We don't have that feature, but good point. We should probably add it sometime in the near future. Actually, it shouldn't stop you if you want to try it out, because the stream creation is pretty simple if you have a publicly for you available Kafka cluster with a dedicated host address and port. So the stream processing is a function of Memgraph only? No, of course not. You have a few other solutions you can use as well. What sets Memgraph apart is the in-memory architecture. So the stream processing is done by an in-memory graph database. For example, you can also use Neo4j to do the stream processing. It has a few other use cases where it's better, and you can definitely check out all the other alternatives if you have some other requirements. Is this a Magnimind event? I love those guys. Yes, this is a Magnimind event. I was considering an application immunology using a graph with fuzzy relationships and properties. Is this a good technology for such an application? I know about fuzzy computing, but I actually haven't seen it in graphs so far. So this is actually a first one from me. Actually, the first time reading such a question. I'm not sure if you left any contact details here in the chat. I can definitely do some research and check if this will be a good application of it. But if you leave me any kind of contact detail, Twitter, LinkedIn, email, and so on, I can get back to you after I check. Sorry for not having the answer on the spot. Is the session recording going to be available afterwards? Yes, it will be available on the Magnimind YouTube channel, which I already subscribed to, and you should as well. Joking aside, I saw there are quite a few very cool topics being discussed on the YouTube channel, and I will probably watch a few of them myself. Can you provide some insight on scale of Memgraph in terms of dataset size? Because it's in memory, it of course takes up RAM. The largest graph I have created and ran on my laptop was around 20 million relationships and around 4 million nodes. And it took up around 7 or 8 gigabytes of RAM. You shouldn't experience any problems with hundreds of millions of nodes and relationships. But for larger use cases, when we're talking about hundreds of billions or even trillions, probably not at this point. We are releasing a new feature this year, distributed storage and distributed computing. So then even trillions will definitely be manageable. Are there sample code? Yes, of course. This GitHub repository contains the demo application I was showcasing. So you can clone the repository, fork it if you want to make any changes. And here are in the instructions on how to run it. If you clone the repository, just position yourself in the root and run this script. It will use Docker to start all of the necessary services. And once they are started, you can just fire up the front end again with Docker. The great thing is that the only prerequisite for the whole application is Docker and Docker Compose. So once you have them installed, everything else will be pulled from the internet, the Memgraph packages, Kafka, and so on, and Docker will take care of everything. Aside from this, there is another cool code example here in this repository. This is a Jupyter notebook that analyzes the same data set. So again, the only prerequisite is actually Docker, aside from, of course, Jupyter in order to run the Jupyter notebook, and the Python libraries you need to install. So GQL Alchemy and Pandas. Actually, Pandas was only used to display the CSV file, so you know what a data set is. Through this Jupyter notebook, I show you how to connect to Memgraph with GQL Alchemy, how to define a graph schema using Python classes, how to create relationships and nodes using Python constructs. You create instances of these classes, and then you can save them to the database. This is an example of how it's saved using the object graph mapper. And this is the same example, just with the Cipher query language. So you can choose both approaches. Importing the whole graph from a CSV file. So these are the tweets that were scraped from Twitter. And with this query, they are imported in the graph database. And yeah, here we perform graph analytics. So we traverse the graph. Here we calculate a PageRank value for each node and return it here in the script. And this was another interesting thing. You can use this language. It's called graph style script to style graphs in Memgraph. So the sandbox I was showing you was the Twitter Christmas network. I executed this query and I can apply this style. Okay, I have some error somewhere. Wasn't prepared for this. Sorry. You can try it out yourself, maybe. But yes, this is probably a good example of code. How fast is the stream processing, or what kind of data can be streamed real-time reliably? I mean, currently we support ingestion of JSON messages, Avro, and Protobuf. So I will assume this kind of data can be streamed in real time reliably. You can, of course, have fail safes in case the data gets lost. You probably should also store it somewhere else. So don't get me wrong, Memgraph is a graph stream processing engine. You use it to analyze the data and to get insights from it. The data is also being saved to Memgraph as well, but it shouldn't be your source of truth. The data should be, if you need storing, long-term storage, you probably need to store it in a relational database or something like that. Thank you for the email. I will get back to you on the question of fuzzy graphs. And does Memgraph support Neo4j only? If you mean the Cipher query language that Neo4j uses, then yes. The only way to traverse the graph and to run graph algorithms is through the Cipher query language. And an alternative, of course, is to do it programmatically, to use drivers to connect to the database from the programming language of your choice. But then again, you are executing Cipher queries to get the results and to perform algorithms. The only exception is Python, where we have the GQL Alchemy library, where you don't have to use Cipher, you can use it instead, and Python constructs instead of Cipher queries.
Great. Thank you, Ivan. It's a great presentation. I find it really useful for many work we are doing. Thank you. Thank you for everyone listening. They were good participants. Stay till the end. It's fantastic. Hope to see you in our future events. Appreciate your time.
Thank you very much for having me here. There were quite a few questions, a lot of people joined, so I'm very thankful for the opportunity to share something I have learned while developing this app.
It's great, and many will watch it from YouTube, so it's great. Thank you. Have a good day. Good night there.
You too.
Bye.
Bye.